Total internal reflection and lenses. Here are your priming questions. So for total internal reflection, we have a light source that is going to be in a higher index going to a lower index. So in this case, let's say we have a light originating in water going into air. So this is going to be slow to fast from water to air, which means that this is going to be moving away from the normal. So it's going to be looking something like this. And so for the concept of total internal reflection, this is the idea that we are going to be moving this light source away from the normal, which means that it's going to be continuing to refract away from the normal. And at some point, when we keep moving this refracted ray will now move parallel to the surface. And if we continue to move this, it will then undergo total internal reflection. And so the angles here and here are going to be the same because it's a reflection, but it happens because of the refraction of the light and using the slow to fast and fast to slow acronym. And so this is another way of looking at it. So when we have this here, if we have it, it'll go straight out if we don't have it at any angle relative to the normal. And as we begin to bring it closer and closer to the surface, so increasing the angle from the normal, at some point it will then reach a critical angle, which is shown here at the bottom with this dashed line. It will reach that critical angle where the light will go parallel to the surface, and if you extend it beyond that, increasing the angle from the normal, it will then undergo total internal reflection. The way to find that critical angle is with the equation below. And so for our definitions, you can read that there. And the requirements are a higher index to a lower index reading. So it's going to be a slow to fast. And so here is the math shown for this. So for the critical angle, this was where, if we go back over here, that's the angle here for when the light refracts parallel, which means that for our equation using Snell's law, n1 sine theta 1 equals n2 sine theta 2, our theta 2 must be 90 degrees because it's parallel to the surface, so it's 90 degrees from the normal. And so we have n1 sine theta 1 equals n2 sine theta 2. We have theta 2 as 90 degrees, and sine of 90 is going to be 1. And so that means n1 sine theta c, the critical angle, is equal to n2. We rearrange this, so we divide it both sides by n1, so we get sine theta c is equal to n2 over n1, which leaves us with theta c, our critical angle, is equal to the inverse sine of n2 over n1. And that's to find the critical angle for total internal reflection. So I want you to try this problem. It's going to be easier than you might think. Plug it into the critical angle equation to see if you can find the critical angle for diamond to air. Now, there are some pretty interesting applications for total internal reflection, and these are used in some pretty nice binoculars. And the reason why they're used for this in binoculars is to reduce the amount of light that is coming in from the sides and to get the light that is only coming in from where you are looking, so it gives you a clear image with better contrast. Some other applications are in fiber optic cabling. We actually have fiber optic cabling on campus that we use for our internet as well as for our internal network. And in this case, the data isn't sent as electrons through a copper cable, like our Ethernet cables. It's actually sent through these packets of light that are sent through these fiber optic cables. And so the light bounces around inside of the fiber optic cable, keeping it inside until it terminates at each end where you can send your data. Now, lenses. Lenses are very similar to mirrors in terms of the equations. The mirror equation is also what we call the lens equation, and magnification is the same. There are a couple of things that we want to keep in mind, though. We have convex lenses, and for this we're going to use what we call double convex, so it's convex on both sides, and this is going to be what we call a converging lens, and when it's converging, it has a positive focal length. Concave lenses, on the other hand, are diverging, and these are going to be double concave, and these will have a negative focal length. A big difference here that I want to emphasize is where the real image is formed. For lenses, the real image is formed on the other side of the lens. For mirrors, the real image was formed on the same side of the mirror as the object. Now, for lenses, the real image is formed on the opposite side of the lens as the object. The virtual image is on the same side of the lens as the object, and remember, this was opposite for what we had with mirrors. So let's look at some ray diagrams, and you will be surprised at how similar the rules are for lenses compared to mirrors. And so for this, I'm going to start drawing my rays, and we use the same ideas. So I typically start with my parallel, and for this, we are simplifying some things. In this case, we are going to assume that we have what we call thin lenses. Now, I've drastically increased the size so you can see that this is a double convex lens. But for our drawings and for our math, we're going to assume that it refracts at the center mark of the lens. And this keeps things simple for our ray diagrams. And in this case, what you'll also notice is in terms of these points, we have our focal length, or this will be our one focal length. This will be twice the focal length, and so we have 1f and 2f positions. And you see the same thing for the other side over there. Now, this is a simplified diagram, and this is to give you a simple idea of this. A parallel light ray, when it hits the lens, it's going to refract and go towards the 1f. The second ray that you can draw is going to be through the 1f, and then it's going to be parallel. And you can already see that the image is going to be formed over here, and so I can go ahead and add this in, and we can go ahead and come up with our descriptions. This is going to be a real image, it's going to be inverted, and it's going to be reduced. Now, what's interesting about lenses is that we have a third line that we can draw, and it actually makes things easier, and you can check your work with this. And this is another special case. And what you can see here is I've simply drawn a straight line through the very center of the lens. And that's the special case. In the case of lenses, if you have a light ray that is going through the center of the lens, it will pass straight through. And that's a quick way to check your work when you're doing your ray diagrams. We can do the same thing over here. I'll do another practice, and then I'll leave you off with another one to try by yourself. So parallel, then through your F1, and then we have through our F1, and then parallel. And I didn't draw this one long enough, so you can see that there. And so, if we were to put the image here, we would see it like that. And so if we have our object between our 1f and 2f, we can see that our image is going to be inverted, real, and enlarged. And again, we can do our third ray to confirm, so that'll look like this. And I want to see if you can draw a diagram for that one. We'll check that one in class. And the next one I want to show you is this one, because this one is a little bit different. Same principles, but it's going to look a lot more complicated. In this case, we again start with parallel to the 1f. And in this case, similar to when we were working with our mirrors, we have to do an extension from the 1f, in this case, to look like that. So it's as if it goes from the 1f, and then it goes parallel. And what you should notice here is that these are diverging to the right, which means that they will converge to the left. And so now we need to draw our virtual rays as extensions of the refracted rays, and it'll look like this. And so what that means is our image is now formed on the same side of the lens as the object, and it looks like this. And so this image is going to be virtual, it's going to be upright, and it's going to be enlarged. All right, let's keep moving on. Now, for diverging lenses. These are going to be where the focal length is negative, and remember these are double concave, so it's concave on both sides. So let's take a look at this. If we have our object here, the principles are going to be very similar, and let me use a solid line. So we have our line parallel, and again we go to the center, and in this case, because they're diverging lenses, these will diverge from the 1F. The next one is going to be going towards the other 1F because our focal length is negative, so we use this 1F, and then it refracts parallel. And what you'll notice is that these two lines are diverging, so that means, once again, we draw our refracted rays as extensions towards the other side, and you can see where they converge, and this is where our image is formed. So for our diverging lens, for this object, we would say that this image is virtual, upright, and reduced. Now see if you can apply that to this one, and then to this one. And here are your priming questions again.